differential geometry. We will talk about differential geometry. So here it includes two words. One is geometry and another one is differential. Geometry means originally it was considered as study of earth. Study of earth, in which they used to study size, shape, and position of objects around the earth. Objects around the earth. So this is originally called as geometry. So now coming to differential geometry. Differential geometry is nothing but a sub-branch of geometry. Which involves the techniques of differential calculus as well as techniques of differential calculus as well as integral calculus. Integral calculus for solving problems in geometry. So this is about differential geometry. So it gives an introduction to differential geometry. Now let's move on to the next concept, Euclidean space. Euclidean space. So it involves two words. One is a space, one is a Euclidean. Space is nothing but three-dimensional structure. So it involves three variables. So the three-dimensional real space is given by R3 is equal to the set of all three tuples such that the points A, B, C belongs to the set of real numbers. Here it is noted that the real numbers, elements of real line, sometimes called as scalars. So we are there in space. Space is a thing about three-dimensional structure which involves three variables, and the three-dimensional real space is given by the set R3 is equal to the order triple ABC, such that the entries ABC belongs to the set of real. See here in the Euclidean space, the word Euclidean is there. So we have taken justification for this. Since we have R3 as a real space, suppose this real space is equipped with Euclidean metric, then this together is called Euclidean space. So here we can think of what is metric. So this metric is nothing but it is a non-negative function which describes the distance between 2 points. Here we are there in 3D space. So the distance between 2 points x is equal to, which is the order tuple, x1, x2, x3, and the another point y is equal to y1, y2, y3. The distance between them is given by d of x comma y is equal to summation from I is equal to 1 to 3 yi minus xi to the power 200 root. So this is nothing but the distance between 2 points. Now the real space R3 together with the Euclidean metric. Real space R3 together with Euclidean metric which involves the function distance function d from r power 3 cross r power 3 to r, which is defined by d of x comma y is equal to under root summation I is equal to 1 to 3 xi comma yi whole square or yi comma xi whole square. So this is about Euclidean 3 space. So this is Euclidean space or Euclidean 3 space. Here Euclidean space is also called as Euclidean space can be called as Euclidean 3 space. Is denoted by E3, which is same as the real space R3 together with the Euclidean metric D. The points in E3 are called as three-dimensional vectors. Now, how to find the vector from the point P to the point Q, where P is equal to x comma y comma z and Q is equal to x dash comma y dash comma z. Now the vector u from P to Q is given by the order tuple u is equal to x dash minus x, y dash minus y, z dash minus z. This is how we will find the vector from the point P to. Now let us study operations on vectors. So the basic operations which are to be performed on vectors are, the first one is addition of vectors. Second one is subtraction of vectors. And scalar multiplication. To a vector. So coming on to the first, addition of vectors. How to add two vectors? Suppose we have two vectors, u is equal to x, y, z and v is equal to x dash, comma y dash, comma z dash. Then the addition vector of these two is given by x plus x dash, y plus y dash, z plus z dash. So this is the addition of two vectors. This can be geometrically viewed as, suppose this is a vector u and this is a vector v, then the sum of these two vectors is given by the parallelogram law of addition. So this gives the vector u plus v. So this is how we will add two vectors. So the next one is subtraction of vectors. So we are having vector u as x comma y comma z and vector v as x dash comma y dash comma z dash. Then the difference between these two vectors is given by x minus x dash, y minus y dash, z minus z dash. So this can be geometrically viewed as, suppose this is u and this is v, then minus v is, so in the negative direction, this is minus v. So from the parallelogram law of addition, this is u minus v. This is how we will find the difference of two vectors. Next, scalar multiplication. to a vector. So let us consider a scalar, which is alpha belongs to the set of real numbers, which is called as the set of scalars. Now the scalar multiplication to a vector u, this is alpha into x comma y comma z. This is equal to alpha x, alpha y, alpha z. This is how we will find the scalar multiplication for the vector u. Similarly for vector v, this is x dash, y dash and z dash. This is alpha x dash, alpha y dash, alpha z dash. This is how we will find scalar multiplication to a vector. Till now we have studied the operation on vector. Now let's look into the structure of Euclidean space. The structure of Euclidean space. Euclidean space E3. So what it will be? So as E3 involves vectors which are in terms of order triplets and are from the real space R3, and in R3 addition of vectors holds good, and scalar multiplication to a vector also holds good. That means if suppose u and v are two vectors, then u plus v is also a vector which is also in R3. Suppose alpha is a vector scalar from R and u is a vector in R3, then alpha u also belongs to R3. So here in E3, as we are having E3 as the real space together with the metric D, in E3 also for u v belongs to E3, u plus v also belongs to E3, and for alpha belongs to R and u belongs to E3, alpha u belongs to E3. So therefore, by two-step test of vector space, E3 is a vector space. Now, so let us look into 0 of E3. Here the 0 of E3 is the order triplet 0, 0, 0. As it is a vector space, it should involve 0. So 0, 0, 0 is a 0 of the vector space E3. Now let's look into one more definition, that is natural coordinate functions. So it involves three terms, natural coordinate functions. Coordinate function, so it means it involves some coordinate system and that should come naturally. So as we are studying on E3, means three-dimensional space, our coordinate system is three-dimensional system which involves x direction, y direction and z direction. So here these three systems x, y, z are called natural coordinates. Now if suppose we consider any point P which is a order triplet and which is in E3, then P1 is nothing but the x coordinate of the point P. We can write it as x coordinate of the point P is P1 and y coordinate of the point P is P2. And likewise the z coordinate of the point P is P3. So we can replace this xyz with x1, x2, x3 because if we have more dimensions, then we will be confused what to take for variables. Therefore, I will take x as x1, y as x2, and z as x3. Then we have x1 of p is equal to p1, x2 of p is equal to p2, and x3 of p is equal to p3. So therefore I can rewrite the point p as, so it was p is equal to p1, p2, p3. So this can be written as p1 is nothing but x1 of p, and p2 is nothing but x2 of p, and p3 is nothing but x3 of p. So here these three functions x1, x2, x3, they are called as natural coordinate functions. Natural coordinate functions. Therefore, any point in E3 can be written with the help of natural coordinate functions at that point. So this should be remembered. This is the representation of the point P in terms of natural coordinates, natural coordinate functions x1, x2 and x3. Now let's move on to the next concept, which is nothing but differentiable functions. Differentiable functions of class C infinity, or it can also be called as infinitely differentiable functions. So let's see what is the definition of that. So, a real valued function f, which is taken on E3, f on E3, as we are considering only Euclidean 3 space, on E3 is said to be differentiable infinitely if means provided all partial ordered derivatives, all partial derivatives of f, which are of all orders exist and should be continuous and are continuous. So for a real valued function to be infinitely differentiable, all partial derivatives should be exist, and these partial derivatives for all should be continuous. So these are infinitely differentiable functions. Now we will see another concept, addition of differentiable functions and scalar multiplication and multiplication of differentiable functions. Addition and multiplication of differentiable functions. So if suppose we are having two differentiable functions f and g, then the sum of these two is also differentiable function, and the product of these two functions f into g is also a differentiable function. So suppose we want to find the sum of differentiable functions at a point P, then what we can do is first we have to sum these two functions and we have to find the function value at the point P. So this can be equal to f of p plus g of p. For multiplication, so this is same as f of p into g of p. This is how we will find the value of the function, value of the sum of the two functions at a point P, and value of the product of two functions at a point P. So this is all about addition and multiplication of differentiable functions.